the same set of equations, but instead of having p of them, we have p minus 1 of them. And then you can just keep doing this process. Then you have p minus 1 of them. You can do it again and get down to p minus 2 and so on until you're down to the one adjusted effect that you want, and then you have it. So in other words, think of it as follows. If we want an adjusted relationship between y and x, keep taking residuals over confounders for both and do regression through the origin. And I would just say the order, once you remove the linear association of y, then x is the same as, removing the linear association of a, then b is the same as removing the linear association of b, then a. So the order doesn't matter. And we know that. We can prove that. It doesn't matter because our choice of doing p first in that equation was arbitrary. And I would just note this isn't a terribly efficient way to get estimates. It just shows how to do it without using any linear algebra. But you can get it in a more efficient way. But let's actually do it with R just to prove to ourselves that it's the same. So here I've generated 100. X is random normal, and then x2 is random normal, and x3 is random normal. And I want my y, all my slopes are just 1, and I have an error term of 0.1. And I want the relationship between y and x having gotten rid of x2 and x3. And because I don't want to just keep taking residuals, why don't I just define my residual function as it takes a and b, and then it's the residual of a having regressed out b. So a minus some a times b divided by some b squared times b. And so my residual of y, if I want to get rid of both x2 and x3, I would take the residual of y, taking out x2, the residual of x3, taking out x2, and then take the residual of that whole thing again. And that would be the residual of y having taken out both x2 and x3. And here's the residual of x having taken out both x2 and x3. I'll take out the residual of x2 and the residual of x3 given x2, and then I'll take the residual of x with x2 out and the residual of x3 with x2 out and the residual of those two, and then I'll do the regression through the origin slope, and I get 1.04, right? Now, notice I didn't include an intercept in this fit. So if I'm going to try and show that it agrees with R, I need to remove the intercept. So I'm doing coef LM, and I'm going to remove the intercept just so I'm fitting the exact same model. And notice it gives me the same number. R doesn't do it this way. It does it a little more efficient way, but it just shows you that it gives you the correct answer. I just want to show quickly that order doesn't matter. So here I reverse the order here and look at how I define these EX and EY. Look at how I defined it now. I do X3 first and then take the residuals again, and I get 1.04 again. Okay. And then also, let me just show that you could do this in R by, let's say, take the residual of y having gotten rid of x2 and x3, and the residual of x having taken out x2 and x3, and then do your own regression through the origin, or you could do lm minus 1, and you get the same answer. Okay? So again, just showing that adjustment is the process of iteratively taking residuals. Let's go over how you interpret the coefficients real quickly. So again, my expected value of my y, given a particular set of values of the regressors, is exactly this relationship, right? We've gotten rid of the plus e part. So imagine if you take this first regressor and you evaluate it at x1 plus 1, holding all the rest of them fixed at their values, versus this guy where x1 is held at x1 by itself. That is this equation is this guy right here, and this equation is just that guy right there. Do the arithmetic, and it works out to be beta 1. Okay, so what did we do? So all we did was increase x1 plus 1. So the interpretation of a multivariate regression coefficient is the expected change in the response per unit change in the regressor, but the important part, don't forget this part, holding all the other regressors fixed, right? So if we're adjusting for smoking status, it's like we're holding smoking status fixed. Again, we're assuming that the relationship between the response and the regressor is constant across smoking status, right? Because we haven't put in any interactions, but that's the idea of what regression adjustment is doing. So let's go over a couple other odds and ends just so we know. Our model is this guy plus the error. We tend to assume our errors are IID, normal 0 sigma squared, at least in this class. Our fitted responses are nothing other than putting the fitted coefficients in. Our residuals are just going to be the difference. Our residuals are going to be the difference between our fitted, our fitted y and our actual observed y. Our variance estimate is just going to be the average squared residual. We're going to lose some degrees of freedom for all the parameters we had to estimate. We had to estimate p slope parameters, so we divide by n minus p instead of n, but it's still, this shouldn't be a great leap from what you already know and do from linear regression. To get predicted responses, we're just going to plug them into the model. We have a prediction interval. It's going to have a +1 if you want a prediction interval, and it's not going to have a +1 if you want the confidence interval for the prediction surface. Coefficients have standard errors, right? And the standardized coefficients, these guys, beta k hat minus its true value divided by the estimated standard error, are going to follow a t-distribution with n minus p degrees of freedom. And then again, the predicted responses have standard errors, so we can calculate expected response intervals. So it's all the same as simple linear regression. So it's sort of like you did some training, some drills on simple linear regression, and now we're at the main event, linear models, and you're seeing how most of these ideas extend very easily. So let me just sum up linear models, because I think linear models are very important. In fact, I think linear models are so important that I would call them the most important applied statistical and machine learning technique by far. That nothing else even comes close. And I'll just name off the top of my head, when I was writing these slides, some of the amazing things you can accomplish with linear models. One thing is you can decompose a signal into its harmonics with linear models. And I'll do an example of that just for fun later on at the kind of end of the class. But the so-called discrete Fourier transform is nothing other than a linear model. Now, granted, you can fit it a lot faster than especially than the way we taught today, but it's nothing other than a linear model where your x terms are a bunch of trigonometric terms. So we can decompose a signal. For example, you pluck a guitar string at A on the A string and record it, digitize it, chop off just so that you just get where the string is playing the A, pass it through a linear model with the correct terms, look at the squared coefficients, and you'll find the one at the perfect frequency of 440 or whatever it is for A will be the one that's significant. Okay, you can flexibly fit complicated functions, right? So if you have data that look like this, like that, and you want to fit something that's not that complicated, but you want to fit something like that, let's come up with something more complicated, something like that. You wanted to fit something like that, you could do it. You can fit factor variables, so like a treatment effect, as predictors. You can uncover complex multivariate relationships with this response, and you can build accurate prediction models. Granted, a linear model is not going to do as well as some super complicated random forest model or whatever, but it's very interpretable, right? Linear models are wonderfully interpretable. So if you're going to stray away from linear models for some complicated machine learning technique, you're giving up a lot of interpretability for probably for better fit, but you may not be getting that much better fit for the trade. So they are great technique to learn. I think they're wonderfully important, and they have so many amazing applications, and that's why you find, basically either linear models or maybe statisticians have rebranded linear systems, but you find them rediscovered in all different sorts of engineering and mathematical fields. Because the idea is just the idea of decomposing things into a linear system is just an intrinsically useful idea. So we'll cover lots of different ways to utilize this kind of model in this class.